Hi, everybody. We now come to section 5.5, substitution. More specifically, it's called u-Substitution for integration. Now, this is one of the most practical skills that you will learn because about half the time you integrate something, you may end up doing u-Substitution. This is very much like, you remember the chain rule, you use it so often now. And it is actually the opposite or the counterpart of the chain rule. So this u-Substitution, I think you will really like it. All right, so let's do that in section 5.5. Okay, so let's start with this function, x squared minus 3 to the 6th power. What kind of function is this? You do have a composition of two functions, correct? Right? You can say y is equal to f of g of x, where gx is, what's the first thing you do? This is the inside function, x squared minus 3. And then f is the outside function, which takes that to the 6th power. So that's something that you can do now, right? You can decompose this into two functions whose composition is actually this, right? So you learned that dy, this is what we called the Leibniz notation of the chain rule. Dy dx is dy du times du dx. What in the world is u? That's g of x, right? So what we said here is f prime of x is, and this is the non-Leibniz notation, the Newton notation, and that says it's f prime of u, right? And that's dy du times u prime of x. And so, of course, this is f prime evaluated at g of x times the derivative of g of x. And this is what you have been using as the chain rule. And that's great, okay? And you realize now experienced that you have used this over and over again. In fact, you probably use this every day now, right? Perhaps more often than when you watch TV. Okay, so for instance, you can take the derivative of this. It's what? 6 times the blob to the 5th power. And the blob is the inside function. That is the u part, which is the, basically what we said is you take the derivative of the outside function evaluated at the inside function times the derivative of the inside function. Is that right? So you can call this 12 x times x squared minus 3 to the 5th, right? Okay, so you can do that. All right, now every time you have a differentiation rule, you can also change that into the integral, right? Integral formula or integral statement. And so what is that? Well, if you happen to come across this integral like that, okay, you could now take the derivative of, well, you can find an antiderivative of this. You can say, because we have done this, right? This is a complicated looking thing, but you could say, well, you know what? We know the answer to this. This has to be the function y plus c, okay? No problem here, right? Or is there a problem? What happens if you were given this? Can you come up with this by just thinking this whole thing in the opposite direction? Well, so remember we use this u as a sort of an intermediate, variable. And so maybe we can do something like that. And that's exactly what we will do. This section in the book, section 5.5, is actually called substitution. I mean, that's a simple enough term, substitution. They should be a little more specific. I mean, substitution could mean a lot of things. What they mean by that is integration by u-Substitution, okay? And that's exactly what we will do. We will introduce what is called u, even though you don't see any variable called u in here, okay? And so here's what we will do. We will take, let's see, maybe the inside function here. If you can identify a new variable u, which is exactly our inside function, right? U was always an inside function, I feel funny to say u is or u was, but that's what I'm supposed to say here. Right? U was an inside function, and so I'm going to let u be x squared minus 3. And sometimes it works, sometimes it may not. The reason it works this time is because, oh, by the way, you write, the next thing you write is du dx is equal to 2x, right? But instead, I want you to write du is equal to, you write the differential because, and this is one of the reasons you'll see a differential here at the end. Du is 2x dx, and this is the correct statement. This is called the differential. Remember, instead of writing this as the derivative, du dx is 2x, we can write this whole thing in the differential form. Du is equal to 2x dx. Now, you actually see 2x dx in here, or do you? Okay, let's take a look at this. My computer is having a little issue. Okay, so if you say du is 2x dx, you can also write this as, now do I see 2x dx? Well, I almost do, right? So I see something that looks like 2x dx. It's what you see is, well, here's 2, here's 2. It's 12, but 2x dx. So we want to identify u, the interior or the inside function, in such a way that du is also a part of this integral. All right. So easily you can write this as 6. Okay. And of course, it's not 6, it's 12, right? So you can write 2x. That's it. All I have seen so far. All I have written so far is 6 times 2x, which of course is 12x, right? I just wrote this in 2 different ways. So, I mean, 2 different parts. So 2x dx is a part of this integral, integral. And so now I have 6 and x squared minus 3 to the 5th. Okay, now, do you agree that I did not essentially change anything? The integral is still the same integral that I was asked before, right? But look, here is the power of the u-substitution. Once you correctly identify u and du, okay, you notice here, this becomes 6, and then this is, of course, u, the inside function, 6u 5th du. So I have completely rewritten the statement or the integral in terms of u. No more x, just u. Okay, sounds romantic. No more of my x, it's just u. And then you write this. Of course, the answer is this is u to the 6th, right, plus c, because the derivative of this is 6u to the 5th. Exactly is that's exactly what you see here. Now, of course, u was not a part of the original question. U was something that I made up, right? So I am going to have to write my answer in terms of u, not u, but x. And so this will be x squared. Remember, u was x squared plus 3 minus 3, 6 to the plus c, which is obviously, I mean, that's my answer, right? Because we knew this, we started with this function and took the derivative, and now we're trying to find the integral. So this whole thing is called the u-substitution. All right, let's review this. Let's stop and reflect on what we did. We find an appropriate u, the inside function, in such a way that if I write du in terms of dx, that's the differential of u with respect to x, you actually see that as a part of the integrand. All right, and in this case, you had 12x dx, so I can write a part of 12x dx as 2x dx, of course, times 6, right? This will allow us to rewrite the entire integral in terms of u, not ever using x. Okay, you can't have any x in here. X and u don't mix up, right? Okay, I was going to make a pun, but that's okay. X and u don't mix up, and so you just write the entire u integral in terms of u, and once you solve that in the world of u, okay, now of course you have to go back to the world of x, because that's where it came from. The person who asked you this question has no idea what u is, so you can't leave u in the answer, right? So that is what you want to do. Now there is another way some people do this. I don't recommend this, but at this point, what some people do is they solve this for at this point, you can say du is equal to 2x dx. Some people just want to solve this for dx because that's what you see here. Dx is equal to du over 2x. Like I said, I don't recommend this, but you may see some friends doing this because you see dx in here. And so if you do that, here's the way, again, u is still x squared minus 3. So those people who will learn to do it this way would tell you, hey, look, this is the original question is this. And so this is 12 x squared minus 3 to the 5th. And then, of course, you have dx, right? So they will write something like du over 2x, and this cancel. And then this becomes 6 because you cancel that. And then, of course, this part is u, right? And of course, the problem is going to be exactly the same as, what you have here, right? So that's okay. Some people want to solve for dx. Again, personally, I don't recommend you do that. But I think this is the most traditional or the most standard way of doing u-substitution. So I will be using this notation, the differential notation, and I will look for this expression 2x dx or whatever du is over here. And that's what I am going to do here. All right, this is the first example. Once you see a few other examples, you will know exactly what to do. And not only do you understand it, I think you are going to really, really like it. And you're going to be using this all the time. All right, so how does it go? The u-substitution in the more general form is this. Basically, what you should have here, and you can't always use this, of course. You have to have some sort of a complicated thing where you have a composition of two functions as the antiderivative. That's when it works, because this whole u-substitution, as you can see, is depending on the chain rule, or it's based on the chain rule. And this is what you will do. This is the kind of situation, this is the kind of integral for which u-substitution will work. F prime of gx times g prime of x, and this just becomes f of gx plus c. Now, what's u? This is the part I am calling u, right? And so this is u prime, and this is f prime of u. And if you look at this, this is exactly the chain rule, right? So that is the basis upon which u-substitution is justified. And but make sure when you pick your u, okay, so find u so that du, which is g prime x dx, is also there. And if it's not, you can find it. All right, so for instance, you can do this. Let's do x squared e to the x third dx. Okay, so can you find Waldo? No, can you find u? Can you find the some appropriate u so that the u-substitution method would work? Okay, so you look at this, it's e to the x cubed. Looks like what you do first is x cubed, right? And then you take e to the power. And so u is almost always that inside function. In fact, u is the inside function. Sometimes, or most times, it's in the parentheses, like in the first case, but not always. But that's okay. I think you can easily identify u should be x cubed. Okay, why would it be a good choice? Because du is 3x squared dx. And you say, well, I don't see 3x squared dx. You're right, okay? Let me go ahead and rewrite this. You don't see 3x squared dx, but you do see something similar to it. You see x squared dx. All I need is 3, right? So you kind of wish that there was a 3 there. And what do you do when you wish upon the star? It comes true, okay? In fact, you can just go ahead and do that because now you can see 3x squared dx, right? Is that legal to do it? Well, not really. You just can't change your problem like this, right? But you could do that as long as this is a constant that's missing. you can just divide by the reciprocal, divide by the same number outside, right? Notice here, I did not change it. I just dreamed, okay? And made this possible. So now I have 3x squared dx, which is exactly my du. What integral do I have now? E to the u, that's x cubed. And then the rest of that, integrand, and differential, that part is simply du. You see how wonderful this looks like? This complicated, integral has now become a very simple integral. What we did is we have this world of x, okay? And we have moved away from the world of x to the world of u, where things are so simple or simple looking, okay? We solved the, see, the problem was here in the world of x. Go to a different world, this problem is much simpler. And then you solve that problem, and then you return to the world of x and say, hey, the world of x here is your solution, right? So this is what happens. In the world of u, this is really easy, right? This is 1/3 e to the u plus c. Remember that plus c. And then you take this back to the world of x because the x people have no idea what u is. And so, the x people don't know who you are. So x is, u is replaced by an expression using x. So this is 1/3 e to the x cubed plus c, okay? If you ever think you made a mistake, or if you may not have made a mistake, but you think, or you may be afraid that you have made a mistake, you can always differentiate this, right? Check. This, oops, it's e to the x to the 3rd power plus c. If you take the derivative, it becomes 1/3 e to the x cubed times the derivative of x cubed, which is 3x squared. These will cancel. That's exactly the integrand you started with. Okay, so this works. And that now you feel much safer, and you can go on to the next question. All right, so let's try. Did we do this? Yeah, I did something similar, but I think it's another. It's a good one to do here. Yeah, let's do this. X squared x cubed minus 3 squared dx. Easy enough. This is a third time charm. I think it's pretty easy to detect or to figure out what u should be, right? There's an inside function, x cubed minus 3, so that the u is 3x squared dx. Okay, don't forget this dx part, because that is a part of what you see after the integral sign. We call this, remember, the differential, right? Well, 3x2 dx is not something you see here. But as before, when you dream, first I just go ahead and rewrite everything, okay? So I know that I didn't change the problem. And I just need that 3, so I will just imagine there is a 3 here. I make the adjustment outside of the integral sign. This is 1/3, and now you see this figure, 3x squared dx, which is exactly my du. So I have u squared du. How wonderful, right? Because that's exactly what we have. Now, again, at this point, you can't have any u in here. All right, I just want you to know, and I will do a problem which you can't solve using u-substitution. But before that, okay, this one is workable. Now I have completely moved away from the world of x into the world of u, and I can solve this. It is what? U squared becomes 1/3 u cubed plus c, right? In other words, this is 1/9. This is technically what's happening here. It's 1/9 u cubed plus c. Now, technically, this is 1/3 c, but I'm not going to make a distinction here, even though I realize, and before you accuse me and write emails, hey, this c is different from this c. I understand that. This should be 1/3 c, but because c is arbitrary, I am not going to distinguish these c's. Yes, I do know that these may be different or should be different, but that's okay. All right, so the answer is 1/9. And again, I can't leave u. I cannot leave any trace of u in my solution. because this was something that I came up with, not the person who asked me the question. So this will be 1/9 x cubed plus or minus 3 to the third plus c. Okay, so that is my answer. All right, check this. Oh, not check. Here's another example. E squared. And yesterday, or not yesterday, some time ago, maybe in the previous section, I said, this function is actually not easily integrable. I don't want to say it's integrable. It's not integrable, but the integral or the the antiderivative is not, it cannot be written as a simple elementary function. Right? There's no easy simple function whose derivative is e to the x squared. Okay, but you say, well, but I can use the u-substitution. Let u be x squared because that's usually the inside function. Du is 2x dx. Okay, the problem is I don't have 2x dx in here. I can even write 2 here and divide by 2 outside, but all I get is 2 dx. See, this thing is missing, right? So I cannot use u-substitution. If I tried, okay, you could say dx is du over 2x, okay, and I will have 2x in the denominator, but see, x is there is no x in here to cancel, right? So if you try to move away to the world of u, you will still have x remaining. And that's a problem when you have an x in the world of new u, okay? So make sure that the limitation of the u-substitution. U-substitution is great. Sometimes you may be able to use that. Sometimes you may not be able to use that, okay? All right, do something else. Again, I have many examples. Let's try this one. I'll do a couple more problems before we move into the next segment of this, okay, of this video for 5.5. All right, what do you want u to be? Do you notice that inside function? Sure, x cubed. This is very similar to the last one, right? Okay, what's du? 3x squared dx. Okay, plus 5 doesn't matter here. Of course, it does show up at the end of the problem. Okay, I don't have a 1/3. And by the way, of course, you don't have to write these things in red as you are doing your problem. I am just showing you different colors so that you can see where everything is coming from. Okay, now I still haven't left the world of u. And by the way, in any line, you should not have any mixture of u and x. Just remember, u and x don't mix. Sounds like you're divorced. U and x don't mix. Just keep that in mind. All right. So then you have 3x squared dx. Ooh, great. All right, awesome. I'd love to see that because du is right there. So this 1/3 came not from the beginning, but because of the u-substitution. What we have is now we are ready to move completely out of the world of x into the world of u. So this is what? U to the 9th and then du. See how simple it is in the world, in the new world. Okay, and then this is what? U to the 9th becomes at 1/10 u to the 10th, okay, plus c. And of course, this is 1/30th u to the 10th plus c, and that is 1/30th x cubed plus 5 to the 10th plus c. Okay, there's no way you could have done this without u-substitution. This is not something easily doable unless you have some kind of u-substitution, right? But once you know this thing, it's very, very simple. All right, let's do a little trigonometric one next. Sine t over cosine cubed. What in the world is this? Okay. And sometimes you do see an integral like this, not just for exercises, but maybe in the real world, in some kind of applications. Okay, so do you see a u, or do you see any potential u such that du is also a part of this? You could do u is sine of t, but then du is going to be cosine of t, and that's in the denominator cubed. Okay, so that's not very good. What you want to do at this point is look for something complicated, like cosine of t cubed. All right, this is what you see in the denominator. So that's what you want u to be, cosine of t. And by the way, if you happen to choose a bad u, then it'll self-correct because you will not be able to do that, and you'll have to start the problem all over again. All right, so let's let u be cosine of t. du is going to be, watch this, not the sine of t, but negative sine of t, right? Okay, now I don't see a negative sine of t, but that should not be a problem. Let me rewrite the problem again, just so you know where everything is coming from. Okay, so I have restated the problem, and now I'm going to make a little adjustment. I need negative sine of t dt. So could I just put the negative sign when nobody's watching? Well, you could, all right, but that's going to change the problem. So, but that's okay. You can easily fix that by putting the negative sign outside. After all, the double negative is positive. Don't tell nobody that. All right, and so it's negative. The integral of, you have u cubed in the denominator, and then what do you see on the top? Everything else is negative sine t dt, exactly what you want. Okay, so this is negative integral of u to the negative third du. How simple, how much more elegant this is, right? Now you have to watch out, you have to add 1 to negative 3, and that's not negative 4, right? It's negative 2, and that has to be in the denominator. Oops. Okay, and then u to the negative 2 plus c. Again, as soon as I do this, I sort of check myself, okay, and ask myself, if I differentiate this, do I get, you know, u to the negative third? And I think I do, because if you start with this, if you differentiate this, I get negative 2 times u to the negative 3, which is exactly what I have here, right? These things, sorry, this is I have here, because these things will cancel. All right, so I know that I am okay. In fact, let me just go ahead and erase everything here, because this is just my work to be checking myself. All right, so I can rewrite this as 1/2, and u to the negative 2 can be written this way in the denominator. So there's my answer. Well, not quite. Remember, I cannot leave u in the problem, right? Unfortunately, you have to go back to the world of x if you are doing indefinite integral. Now, in the next segment, we will be talking about what happens if you are integrating a definite integral, if you're trying to evaluate a definite integral. In the world of, well, not in the world of, if you are trying to evaluate a definite integral using u-substitution, there is a way not to have to return to the world of x. In fact, I recommend you do not go back to your x, because your x could cause trouble. All right, so this is 1/2, and what was my u? That's cosine square t, right? So this seems, you can also rewrite this as 1/2 of what? Yeah, secant square t. Oh, whoa. Did I just forget plus c? That's -1 point on my exam if I forget plus c. If I forget plus c for every single problem, and if I have 5 problems, that would be -5 points. Don't do that. Okay, so it's 1/2 times secant square plus c. That's kind of surprising, because this, you would not have expected this to be the antiderivative of sine t over cosine cubed. But that is correct. Is it right? Okay, let's check. I'm a little concerned. Maybe I didn't do something right. Okay, so if I start with this, which is, by the way, maybe I can rewrite it this way. Let's try to differentiate. Okay, so ddx. Let's ddx this. What you get is 1/2, and then 2 secant t to the first power times the derivative of secant, which is secant tangent, right? And that these will cancel, and so this is what's secant? 1/cosine. That's what you have here, and then you have tangent, which is sine over cosine. These are all t's. Okay, and that's exactly what you started with, sine t over 3 cosine t. All right, so I was okay. Good. Now I can go on. Right, let's do one more before we go to part 2 of the lecture video for this section. This one is slightly different, okay? This one requires an additional step, and this happens sometimes in u-substitution as well. Okay, so what do you want u to be here? You don't want u to be a complicated thing like this, okay? Because then du is going to be, can you imagine if this is your u, then du is going to be 1/2 x minus 1 negative 1/2 power the x. All right, and this is not going to work, okay? You do see this part here, but then you would not have any u in here, so that wouldn't work, okay? But you can let u be x minus 1, can you? And then du is very simple, dx, which you already see, okay? Now this part, just look ahead. This part will be u square root of u to the 1/2 power in the denominator. We can handle that, but we can't yet handle this x in here. Okay, how are we going to express that x on the top? Well, the idea, and this is the new step I was referring to. See, as soon as you write this, okay, and if x appears in multiple places in what you want to do u-substitution on, okay, you can also solve this for x. In this case, x is simply what? U plus 1, right? So this piece of information would actually help us rewrite this in terms of u without using x. See, x is now can be written as u plus 1. And in the denominator, you just have u to the 1/2 power, right? You could just say it's a square root of u. dx is the same as du, right? So this dx simply becomes du. And you say, well, I don't know how to solve this. Yeah, you do, okay? Because it's nicer to have a numerator, which is a sum, than the denominator, which is the square root of a difference, okay? If you have a denominator, which is just one, unit or one term, this can be rewritten, okay? Because see, the thing is, if you have a sum on the top, you can separate this. So in other words, this is what I'm saying. This is the same integral that was asked at the beginning, okay? So it's nice to have a sum on the top, not on the bottom, okay? The bottom, the denominator, that's a sum. It's very hard to do anything with. But as long as the denominator consists of exactly one term, then you can separate, a complicated looking fraction. So what is that? Well, it's u to the first divided by u to the 1/2. That's u to the 1/2. It's the square root of u, what you're watching here, what you're looking at. And then the other one is u to the negative 1/2, right? Okay. Well, I think we can handle this, or you can handle this. This is, you add 1 to 1/2, that's 3/2. Take the reciprocal of that, and that is your new exponent, making sure that when you differentiate this, you get u to the 1/2, which you do, right? Plus, now, if you add 1 to negative 1/2, you get 1/2. The reciprocal of that is 2, and then you just add. So this is your antiderivative of u to the negative 1/2. Again, you can differentiate this mentally and make sure that you get u to the negative 1/2, which you do. Okay, so this is the solution using u, but remember, you can't use u in the final answer. So this will be x minus 1, 3/2. Okay, 2/3 times x minus 1 to the 3/2, plus 2 times x minus 1 to the 1/2, the square root, and plus c. Okay, and there is your answer. All right, I have a few more things to say, and including what happens when you want to use u-substitution in evaluating definite integrals, which is the main part of the second part of section 5.5. But that's going to be on the separate video clip, and so I will go on to the second part now. And you should go to the second part of the lecture video for section 5.5.